right. Thank you very much for having me. My name is Nishant Mehta. I'm at APL, and my team is responsible for developing the render and camera emulator, the output of you've seen in the last few presentations. I'd like to begin by thanking my team, excellent team at APL, Carolyn, Peter, Masad, Steve, Tim, and then and Cheryl Reed, of course, making all this possible. So what I'm going to talk about is the render and camera emulator. It's a tool that was developed to help test the terminal guidance portion of our encounter with Didymos, specifically SmartNav. We've already seen this, so I'm not going to go through this. What I want to point out, though, is we are targeting, or not targeting, I apologize. That's a poor use of terminology. My talks focuses on these phases of the mission, specifically. The target detection, acquisition, scene classification, and so forth. And in particular, we're trying to understand, we have a system called SmartNav developed that you've heard about. SmartNav, which stands for Small Body Maneuvering Autonomous Real-Time Navigation, provides onboard autonomous guidance, navigation, and control of the spacecraft. And this flow diagram is a very high-level functional diagram that shows the various pieces of SmartNav. I'm sorry? Oh, okay. The image processing components and some of the GNC components that belong as part of SmartNav. SmartNav encompasses the algorithms that Lena talked about, the object detection, centroiding, and targeting, all occurring on board the FPGAs. And the GNC system has a couple of components that we consider part of SmartNav, field management system and the guidance filter. This diagram does not include the control systems and all that. I'm going to specifically focus on this box right here. So we've heard about Draco, the imaging system. And the question we ask ourselves, how do we test these algorithms out? How do we test this before we fly? And my team is responsible specifically for the imaging simulations that we use to feed the closed loop sim that Lena mentioned. So the RCE is software for simulate physically accurate scenes of space-based optical systems. For DART specifically, the goals are to cover a large trade space. We want to test SmartNav. We also want to beat it. We want to beat on it. We want to know its failure points, how to make it more robust. And one way to do that is to simulate a whole variety of situations. So for example, we're coming in onto an asteroid. We don't really know what the shape of Didymos B is. So one thing we do during our SmartNav simulations, during our Monte Carlo runs, is vary the shape of our object. We also vary things like the albedos. We vary certain orbital parameters to kind of get a sense for what SmartNav would do if the sun's in a slightly different position when we get there, and so on. And the second piece of this was, want to ensure it runs fast, because we want this to operate in the simulation to operate in real time to support hardware and software testbed simulations that we do at APL, support flight software development and so forth. And just some examples of the rendered imagery. I think Lena showed a version of this diagram right here, where it's hard to see on the screen, but you know, Didymos B is somewhere right in there. I'll just walk through some of the major high-level components of the emulator. Like transport surface modeling, of course, we model a variety of surface fluxance types. Once again, we don't really know what Didymos B will look like, so we want to make sure we cover our bases. Everything from your analytical diffuse surfaces all the way through Hapke type models. And then it was mentioned earlier that we care about, I think it was mentioned this morning as well, when we target Didymos B, we want to hit center of figure. That's our requirement. We don't know where the center of mass will be, but what we can do is we can centroid on, threshold and centroid on the object that we do see. And so part of the reason we saturate, as Lena talked about, is that, or as Carolyn pointed out, we want to be able to pick out the dark side of Didymos B due to Didymos A shine. And that's something we simulate here. In this case, this is just a simple test case where we had a sphere stand-in for Didymos A. And I think we actually used KW4A as a stand-in for Didymos B in this case. Stars and space background. Turns out this isn't terribly important for SmartNav, as it turns out. Our integration times are slow and are fast enough, short enough, that we really don't pick up any stars, which is actually very good for the targeting system. We don't have a lot of confusers in the images. But for, we've been using this to help some of the OpNav testing as well. And we've pulled star data from UCAC4 catalog, did the best we could to estimate the spectral content, quality of the stars and use some data from Gaia to correct those models. Remember, Draco is panchromatic, so it's hard to predict the brightness of a lot of these stars because we just don't have the data on them. We don't have the spectra for all these stars. And we do space background. The folks at IPAC, thank you guys for publishing your data. It's been very helpful. Simulate the optical system, everything from spectral transmission to point spread function, stray light effects, including ghosting, which you see here. I will say that in order to produce this image, we had to really stretch it and really saturate these guys in order to see any ghosting. So we should be good there for Draco does not exhibit much ghosting, enough to affect us. And FPA simulation, noise simulation. As mentioned, Draco has got a CMOS detector. That's what we're simulating for our smart nav simulations. We do simulate various types of shutters. Smart nav will be operating in a global shutter mode, which is our primary simulation. And then various components of the FPA, noise characteristics, popcorn noise, dark current read noise, spatial non-uniformity, and so forth. And dynamics, of course. Apparently, DART will be moving around while we're taking pictures. So we want to make sure we capture those dynamics, everything from the jitter and to smear, moving objects, which hopefully won't have anything else flying through the images. And then we've done some extensive validation work to ensure that the RCE is producing something that's accurate. And I forgot to mention earlier, I want to make sure it's understood that this is really meant as an engineering tool. The output is not meant to, it's meant to be accurate, scientifically accurate, physically accurate, but the goal is to make it good enough for engineering the smart nav system. And that's what we've done. We validated the system against those conditions and ensured that this stellar model is verified against a variety of data sources. Our optical and FPA models look good against engineering data that we have from the Draco team. And we'll continue doing validation and verification work over time as we get more data from the engineering teams. And even after DART launch, as others have mentioned, we'll be doing star calibrations and looking at the moon and things like that. And we'll use that data to feed our system, feed our simulations, and improve that over time. And Lena kind of stole my thunder with the video. I wanted to show this anyway. I'll point out a couple of things. This is 10x real time as opposed to, I think, Lena, yours was 60x. So the last 3 minutes of the encounter. In this particular case, we used KW4A as the primary stand-in, and KW4, Didymos B is actually a scaled version of Itokawa. I will say it's 10x real time. Keep that in mind. You see a lot of bouncing around, and DART really isn't that frantic. It's 10x real time. And we come in and you will hit the target. We're within the last 2 minutes where SmartNav is no longer targeting. Come in and static. Yeah. So, and that's it. Oh, and that static's a joke. Just
Thank you, very cool. We do have time for questions if anybody is interested to ask. I have a question about the testing that you've done. Is this in a way of Monte Carlo type of large number of runs? Okay,
yeah, we do both Monte Carlo and individual runs. We have a cluster on which we run a lot of these hundreds, thousands of runs, varying all sorts of parameters, including, like I said, everything from the physical parameters of the object to certain imager characteristics, focal plane characteristics, optical characteristics, and covering the trade space so that we can ensure robustness.
Excellent. Sounds very well.
All right.
Okay.